very low. You're not, you don't have cooling towers. It's sort of pretty.
The broadcast is now starting. All attendees are in listen-only mode.
But there is quite a bit of evaporation from the reservoirs, and so it actually has the potential to be even more significant than other electricity sources. So when we think of lab buildings and in most buildings in general, the sustainability kind of movement and the rating systems have generally focused on, it's the irrigation, it's the toilets, it's the sinks, those fixtures. In some cases, a little bit of focus on equipment, but the bulk of it has been, on the first three there. But when we take a look at the labs and where water is used, and this is something up until a few years ago, right, it just didn't. In some ways, we weren't asked to think about it, and I think personally I hadn't thought about it, and it really opened my mind to thinking about all these. So well over a decade of working on green lab design, and from a water perspective, thought we were doing great by saving 30, 40, 50% on sinks and showers and toilets, and all of a sudden realizing, that's just scratching the surface of a laboratory facility. And so, the bulk of it is used at the cooling towers. A lot of it's used at the lab processes. And so there really is this kind of holistic need for us to think about, how we tackle this. And, it starts really at that generation side. And, for some institutions and organizations, right, they're generating their own power. Maybe it's cogen, maybe it's coal or natural gas consumed on site. There are cooling towers associated with the building or the campus plant, and then there's the laboratory equipment. So there's this area of opportunity that represents the bulk of lab buildings, and generally, the rating systems and most of us design professionals had really not been paying attention to that, or maybe intentionally working on those elements. Now, more recently, their ASHRAE, as part of the Standard 190 group, has created a water modeling process that looks a lot like the ASHRAE 90.1 Appendix G energy modeling process. And, it becomes very useful to, not just have energy end-use breakdowns, but thinking of water end-use breakdowns. And some of that is directly used in the building and associated with the building HVAC. Some of it is site, irrigation. There might be other processes on site. It takes maybe a little bit more to capture, but we can begin to create this holistic picture and really capture the interrelationships between the two. This is an example from a lab project in Wisconsin. So northern cooler climate. If you look at the inner ring, you can see that the energy end use, the darker blue color there, it's only 11% of the building energy consumption. And so, sort of what you would expect in a northern cooler climate, but it still represents, over 50% of the water use. And, by understanding, what, both the benefit or the opportunity, if I can reduce cooling energy, right, it's good for the building, but it also makes a huge impact on water. And, you can see heating, right? It's the dominant energy end use. But
Paul, if I can just interrupt for one
Sure.
second, it seems like we're having some audio issues that nobody's being able to hear us right now. So I'm just going to put you on hold here for one sec, okay?
Sure.
Paul, it seems like the audio issues have resolved themselves. If you don't mind, would you mind going back to the beginning and starting over? I apologize for that.
Yeah, no, that's fine.
Okay. Thanks.
Yeah. All right. Yeah, my advancement's hung up, so let me Are you seeing any movement in the slides? Or?
No, we're not.
Okay.
Apologize.
No, it's all right. Okay. There we go. We're moving again. All right.
Thank you.
Try this again. So for the objectives, talk about energy and water savings, some opportunities for conservation and in relationship to project infrastructure, understanding the savings associated with plug load management. A lot of that ends up coming back to laboratory equipment. Some of it is just process lab equipment. And I think there's a reality too with high performance research facility or lab design, right? We're putting a lot of great designs out in the marketplace, amongst architects and engineers. And I think in many cases owners are asking for them and yet at the same time struggling to operate them. And so I think it deserves a little bit of time and attention. We'll hit on energy water nexus here today, talk a little bit about progress over the last decade in terms of energy, and a little bit around water, opportunities moving forward, and we'll have some time for the questions at the end. Here, most of the data sources I'm going to use here are drawing from the U.S. I imagine, other than maybe some of the costs, there's, my understanding, there's a lot of similarities in terms of kind of energy sources and just how the systems work. I think there's going to be some strong parallels. So hopefully you still glean something from that. When we look at water for energy here in the U.S., 3 times as much water is used for power production as it is used for public utilities, public water supply. And, it's pretty significant. And, I think when we look at the amount or the cost of water itself, a lot of that is associated with the energy, right? It's the extraction, it's the treatment, it's the distribution, it's the cleanup or processing, and then oftentimes discharge elsewhere. And a lot of it's pumping energy. Some of it is in the process in itself. And so, there's this tie in the, the utility scale has been deemed the energy water nexus, this kind of coupled effect of the more water I use, right, the more energy I'm going to use associated with it. And the more energy I use, the more water I consume as part of that process. So when you look at that grid scale, we've got some different sources of electricity, and this represents, it's sort of I would say it's a muddy process. There's variability against, among types of plant, location of plants, are they rejecting to lakes or pumping water out of the ground? There's a mix. So this data is, it's out there. It's not nearly as rich as some of the other, say energy data we might have around buildings and utilities and even national data. But it helps to create a picture, create an understanding that there is a certain amount of water that's associated with every kWh of power we generate. And hydroelectric, due to the evaporation off the reservoir, right, even, surpasses all those others. So it's a pretty, it's a pretty important thing to understand. And as you can imagine, then if you think about it more at a building scale or project scale, right, every utility grid might, has a different mix of fuels and utility generation. The water story associated with each unit of energy generation varies. And so it becomes something to understand sort of on a project by project basis. When we think about buildings and, our traditional response from a sustainability perspective, much of it, and the rating systems that are out there, most of them are focused on irrigation, toilets, fixtures. There's been a little bit around equipment. But when we take a look at lab facilities in particular, right, we really essentially just been scratching the surface by focusing on those elements. There's a huge amount because of the early energy demands and cooling demands of lab buildings frequently. The cooling tower consumes quite a bit, the lab processes themselves. So, we really need to think about a more holistic approach to getting after water use in those buildings and ideally beginning to capture and think about strategies to do so. When we think about, a lot of institutions or facilities, they might be generating their own power, right? It might be natural gas on site, could be coal on site, there might be cogeneration. But there's oftentimes a water associated with that generation, even at a sort of a campus scale. Then we have the cooling towers, right? They might be at the central plant, they might be building by building, but in many cases, we have quite a bit of water being evaporated to reject heat. And then we have the lab processes. So these are some real areas of opportunity, we've been finding in the marketplace to talk about water in a much more holistic way. I think in the past, one of the challenges has been we've had a lot of tools to do energy modeling, but not do water modeling. And more recently, ASHRAE Standard 190 has had a working group working on a water modeling process that, is mainly focused on kind of, something similar to ASHRAE 90.1 Appendix G energy modeling, where you would, begin to capture in a similar fashion all the building water end uses, and some of those are tied to HVAC, so the boiler water makeup, humidification, cooling tower makeup, but then some of those other factors, the domestic, the irrigation, maybe other water process uses. But ideally, the intent is to create a whole picture so that we can think, as we have been doing for probably 15 to 20 years around energy, about energy conservation measures and different strategies to save energy. We can now think about water conservation measures, and at the same, we can actually model the two in parallel, and so we can get the relationship between, an energy conservation measure and its savings potential for energy, but also maybe impacts on water. So this is an example of kind of taking it down to a very detailed level, but this was a business school project we were looking at in Ann Arbor, Michigan, and thinking about a private office in, say 10 feet wide, by reducing the glass height by a foot, so 10 square feet of glass. We were able to save about 3 liters of water a day over the course of the year. And in my mind, I got to think, well, this is like what someone sitting behind that window at a desk might be drinking over the course of the day. But then it was even more interesting to, see back at the source, back at the utility grid, they were consuming 5 times more water per day to make electricity or to make the energy that was going into the building. And so, it's sort of fascinating as we began to explore via modeling and be able to pull this information out. Right? It's just one more piece in thinking about high performance design and sustainability. Now, here in the States, water rates have been outpacing natural gas and electricity, significantly. The other two have really held much more constant, particularly in recent years, and water rates have been going up dramatically. And what we see is it's not a national factor. It's really a local factor. It's, very kind of municipality by municipality, where, in some cases it might be availability, and in other cases, say Pittsburgh, because they've been relying on 100-year-old infrastructure, and now it's coming to the end of its life where it needs a lot of update. And they haven't been putting money aside, right, to make that investment. So now they have to play catch up. And the same thing is true with the city of Chicago. In other cases, they weren't charging the full cost to ratepayers, and now they've realized they need to. And so it's very localized, and so that's been a challenge, but also an opportunity, project by project, to think about, is this something that really comes into play? Whereas water's been so cheap, maybe here in this locality, right, it's a real opportunity. Now, this was an example associated with a project and some exploration we did of kind of the mid-Atlantic region, or towards the northeast. And, you can see there in the middle, just, some counties that were adjacent to one another actually had pretty significant rate differences. And again, it's the factor of the locality. And, it's something that project by project you can understand, but the data has been thin, right? There's more and more data that's coming. I think our design professionals, and particularly energy modelers and sustainability folks, are beginning to think about water and trying to bring that to bear on projects. So, thinking about projects going forward, I think it's something more and more we can ask those sorts of consultants to help us understand. So hopefully you've got a better picture, I think, of this energy water nexus and how the two tie, and the fact that, as we reduce energy, we reduce water. And so, when we look back over the last decade, we've been making good progress, and maybe sort of unbeknownst to ourselves, right, by saving a lot of energy in many of the buildings we've been designing. Right, we've been saving water, right? We've been reducing cooling tower consumption. We've been reducing boiler makeup. that's a great thing, right? I think, we've made big strides in terms of what has become standard solutions for many laboratory buildings. So I think that's pretty encouraging. I think there's still some room to grow. Right? These are some of those sort of trending systems, both lab and non-lab. Some of those other building types start to spill over. The solutions for those start to spill over into our lab buildings. But we're seeing a mix of more sort of advanced strategies. We're seeing a bigger push for integrating those and thinking about maybe different seasonal modes, maybe having more than one HVAC system serving, a particular program in the building, because part of the year it's really good at one thing, or part of the year it's really good at another. So we're layering strategies on, but we are saving energy. When big elements of that have been air quantity reductions. So considering hoods, the type of hoods, are they variable volume? Do they have, can they go to low flow? That's been a big piece of it. Even from a programming perspective, do we need those hoods, right? We get a lot of projects where you put a lot of hoods in, but eventually, they're sitting there idle, and we could take them out. There are air quantity standards, and so thinking about minimum ventilation rates. So, 10, 15 years ago, many projects were still up at 10 to 12 to 14 air changes per hour minimum, right? Consuming immense amounts of energy, diluting all those spaces. And really, we've seen a big shift where, from an occupied perspective, more and more owners are operating at that 6 and 4 air changes per hour, and considering unoccupied set points that are even lower. We have a much better understanding now of the sensible loads in many of the labs. In many cases, facilities were over-designed, or if you looked at all of the spaces, we didn't need that much cooling capacity. We didn't need our air systems to be so big to provide cooling. And so I think we've got a lot smarter on strategies for reducing air quantity. From a cooling perspective, right, we've seen more and more strategies around decoupled ventilation and cooling, so providing more zone level cooling. Fan coils have sort of been a long-standing option. We've seen active chill beams and some other radiant or convective type strategies come into the marketplace that have, really made a strong foothold in the lab buildings, and in many regions and program mix lab buildings have been able to deliver energy savings. We see demand control ventilation, right? Really looking at what is that kind of sort of real-time feedback. I mean, what should that minimum air change rate be? Should it just be set by time clock or occupancy? Should it be based on actually figuring out what's going on in the spaces? And should we have something that's more dynamic? So ASHRAE and some other organizations, including up in Canada with, say, vivariums, we're looking at alternatives to turn down based on sensing. So there's a lot going on. From an energy recovery perspective, wheels continue to be sort of prevalent in the market, but we're seeing even more advanced runaround loop systems that are coming into play, making really big strides. We see heat recovery chillers, the sort of modular type that are taking advantage of the simultaneous heating and cooling loads that persist in laboratory facilities, right? And providing a piece of equipment that, instead of rejecting the heat via a cooling tower, right, is taking that heat and bumping up the temperature a bit and using it in the building. And so that's a really great example of the energy water nexus, where I've got an HVAC water savings. This is an example, a large 600,000 square foot lab project in downtown Chicago, where this smaller bundle or stack of heat recovery chillers really made a huge impact as sort of a single line item ECM, not only on water but also on energy. So it's been encouraging really to see what strategies have become more and more commonplace, and not just necessarily one of these on even many projects, but we're starting to see many of these layered into lab projects. And that's how we're getting, that 30, 40, 50% savings from where we were a decade ago. And as I said, I think that's great because, unbeknownst to many, right, we were reducing water consumption in the background because we were reducing energy. So it's a really good story there. And I'd say, the way I categorize it, a lot of it has been the low-hanging fruit, that we've been picking. It's stuff that we engineers and the architects really have some control over. Now, going forward, I think it gets a little bit more dicey. Like, it gets a little bit more challenging because it's higher hanging fruit. And if I'll try to walk you through this, but If you think about where we were, a decade ago and kind of our end use stack, sort of a typical, kind of, let's say, column chart from an energy model, right? We had lights, equipment, fans, pumps, miscellaneous kind of electrical loads, in this case, heat recovery chiller. We've got cooling, we've got heating, we might have process steam, right? That was sort of our profile of the building, sort of like an energy fingerprint. In this case, this was a large, kind of taken from a large biology lab building that we see a lot of biomedical facilities with sort of this sort of signature. And when we looked at where we were on equipment perspective, right, we were about 24% of that overall pie. But as the design team, we've wrung out a lot of the opportunity, a lot of the savings, and we've reduced heating dramatically with those strategies I talked through. We've reduced cooling. In many cases, the fan energy has gone down, the pumping has gone down because of that. But we've gotten to a point where there's not much more we can do until we begin to tackle the equipment. That equipment starts to represent almost 50% of what remains. And that equipment, a lot of it here is plug load. There's some process load too. But it's not just the direct component. It's not just, say, your ultra low temp freezer that's plugged in. It's then the fan energy or the pumping energy for your fan coil. It's feeding your fan coils. It's conditioning of outside air that's coming to those spaces to provide cooling. So you have both direct and indirect components. And so really what we started to see is that what remains in this lab equipment sort of opportunity is pretty significant, right? If we can't tackle that, it will be hard to further tackle some of those other end uses. Now, when I started my career, before getting the design side of things, I was working in a chemistry lab and purchasing equipment, and I fully get how difficult it is to think about some of the challenges to tackle lab equipment. I mean, there's been a lack of alternative products, procedural from a procurement perspective. Oftentimes, I just go to a catalog and pick what was cheapest, or go to a vendor they could have something to you tomorrow. Each lab group purchased their own equipment, so there's some real challenges there. There are other challenges from an operational perspective. How people work, how lab groups work, and can they leverage that equipment? Does it have the features that fit with how they work? There's a lack of incentive, right? Most organizations, the lab researchers don't pay the utility bills, and so there isn't an incentive to think about it. In many cases, there's not a lot of data out there. And so when we sort of started taking a look at where do we really begin to tackle this? Sorry, I don't know why it's flashing. Are you seeing that flashing, Martin?
Yes, we are.
Okay. Okay. Very sorry. I'm trying to think. All right, maybe it's calmed down. So, if you take a look at that large mix of equipment, right, it's pretty daunting, right? There's so much stuff here that we're very unlikely to go after. I mean, there's a bunch of stuff that's commodity equipment that, unlikely has alternatives that are focused on energy, that vendors that even know energy is an issue. In many cases, they're smaller equipment. There's specialized equipment, right? It's custom, or it's just unique. It needs to remain on all the time, or it has certain cycles it needs to go through to kind of go through its process, or to be at the ready at all times. And so you sort of take that out of the mix. There's some small energy users that you take out, and what remains is, I think, some pieces that we can really get after. Some elements, at least today, without probably broader engagement of groups like SLCan and I2SL and others that might reach out and engage those organizations, the researchers and vendors, right? Here are some pieces that we can really get after today as designers, as lab planners, as owners, thinking about what would be easier to adapt to, or create incentive programs, or help with procurement. So, I talked about the biosafety cabinets or the hoods earlier, some of the ventilation strategies. So I want to focus on these pieces that I see as process equipment, whether they're kind of electric utility or steam, natural gas based, but I think those are the big pieces. When we look at, I did some kind of local metering with a friend of mine. It's got his own lab, and we looked at some of the equipment, and the minus 80s, right? I think as many of us now know in the industry, right, they dwarf almost everything else going on inside most labs, most bio labs in this instance. And when we take a look at what that might mean, to a building, when we've looked at the direct and indirect use of ultra-low temps, when we've got a linear equipment room in maybe a small freezer farm, right, it can be pretty significant, right, both from an energy perspective, but also, an emergency power, an overall sort of system infrastructure. And so there's some real opportunity there. We've been encouraged to see progress in the marketplace, sort of starting with Stirling engine freezers that came to the marketplace, had significantly better performance than kind of the most of the mainstream vendors. We've seen numerous clients that have adopted those into their fleet. There's a lot of benefits that they have extolled as part of adopting those. But we've also seen that begin to change the marketplace, where we now have some of the more standard vendors that have compressor driven models, now looking at variable speed compressors, offering alternatives in the market, which from an MEP's perspective has been exciting, because now, thinking of open procurement and competitive procurement, now it's not just one vendor, right? We're starting to have 2, 3, 4 vendors that can be in that 40 to 50 to 60% better than everybody else range. And now you can begin to plan, freezer farms or linear equipment rooms with less loading. If, again, you're willing maybe as a project to take, to provide those to users, to say, no, you're not going to bring your old 30-year-old behemoth in that's sitting around half empty and iced up, right? We're going to provide new units, but that's going to allow us to downsize our electrical system, our mechanical system, or, maybe just allows us to provide emergency power to other types of equipment. And so it's been pretty exciting, I think, in engaging owners and researchers to think about what might be a different approach to lab freezers. And, when this is an example, looking at this large project in downtown Chicago, a small fraction of this 650,000 square foot building, it was a freezer farm and then an LER in each floor. And we looked at, freezers that were 50% better, and assumed 75% of those would be those, right? That offered an 8% savings to the entire project, right? Basically getting rid of the glass in its entirety wasn't even 8% savings. So this became, it's funny being an MEP engineer getting excited about ultra low temp freezers, but when I first kind of came on these about 6 years ago, it's just like, oh my gosh, this is about the closest thing we have to a silver bullet for a lot of our facilities, right? It's very, very significant. And so, both it has this energy component, but it also has this water impact, because we don't have to reject all that heat. If we're generating water at a grid scale, there's even more water saved because we're reducing the energy consumption. Now, when we look at that mix of opportunities, data centers is another one, and really computing, right? We've seen different types of sort of trends around computing. The obviously research, most of us have very aware, right? Research has become much more computational intensive. We still see, right, in talking to owners, this, where there was a hope of going to the cloud, there's still so many that are keeping that data in their buildings. They're keeping the computation work in their buildings. In some cases, it's on the campus, it's centralized, but really the pipelines and the quantities generally seem to have been prohibitive to going to the cloud. And so we still see a lot of projects where computational opportunity is significant for us to think about. At the desktop, right, we've got standard workstations, laptops, thin clients. There are a number of things that can be looked at. And again, this is, it can be difficult with researchers. They might be providing computers out of their own budgets. There may not be a standard procurement. I get that there are challenges, but for those buildings that are more administrative heavy, there are things to think about, even from procurement. There are Energy Star and other types of kind of low energy approved or certified products out there that can be purchased. But when you start to get into the bigger computing, we've seen almost a hot aisle, cold aisle strategy just for small server rooms, where they basically have a server closet. We can, instead of having that fan coil mix the heat off the unit into the room, right? We just capture it off the top, go to the fan coil unit and bring air in it. So basically don't water down the cooling you're providing to the space. Let it be as effective as possible going in the front side of the rack. coming out the top or the back being taken away. We've seen facilities then too. So this is an example of that Chicago project. Just by going to the server closets that are doing that, it's a 3% savings. Again, that's more than just going from one good glass to a better glass. So a significant opportunity. Where we've got bigger data centers, right? Looking at the hot aisle containment, the hot aisle and chimney containment sort of approach becomes a significant opportunity. Where in the past we would traditionally mix all the air in that space, and again you had to put in a lot more air because that cold air you were putting was getting somewhat warmed up by the air blowing around in the space, and so it was less effective at doing its job of cooling the piece of equipment. And so now if we can deliver cold air to the equipment and pull the hot air off the back or off the top, right, you can really reduce the amount of air you need. And we had a engineering lab example, significant wattage, watt per square foot of data center, but small relative to the overall building, but it still represented a huge energy impact to that overall project. And by proposing that sort of hot aisle, cold aisle approach, that it's not a co-located data center, it's not what you think of as a big data, but thinking of it in a research facility, right? Thinking of bringing those better practices from the data center industry to our research facilities opened up a lot of opportunity for system sizing savings and cost savings, both from equipment and ongoing utility costs. Now, the last piece I want to talk about is some of the process equipment that lab planners tend to have more of the influence over. We're seeing opportunities with cage wash and tunnel wash where we've got reclaim in many cases by using chill water heat exchangers instead of dumping potable water down the drain to quench these units. There's a significant amount of water that can be saved. So we have both energy and water opportunities with some of this lab equipment. And what I think is interesting is that in the past we always saw water as relatively inexpensive, and often would do energy accounting but not do water accounting and not take into account the water utility. But with rising water utility rates, we see that in some cases we are looking at strategies where if we just looked at energy, right, it's a penalty, right? We're not going to take that approach. But if we take water costs into account as well and look at it in an integrated way, sort of holistic cost accounting, we're starting to make different decisions. And in some cases, this extends to air-cooled chillers instead of water-cooled chillers. It's other types of equipment because of this. So again, it's very sort of localized. I mean, you have to understand the energy rates and the water rates of that particular climate and that particular locality. But we're seeing that it is changing how building design decisions are being made. This is an example from the slide I just showed. This was at the time Pittsburgh, and it was relatively cheap water rates compared to much of the country here in the U.S. And yet, at the end of the day, it's still won out for us. So I think as we, to begin to sum up a little bit of that last section on tackling the 50% and thinking about how we're going to get after, the equipment side of it, and then, which then in turn lets us maybe wring out a little bit more out of the rest of the building end uses. Is how do we do this? Some of it is maybe focusing on certain things that we can focus on now, things that we as designers and maybe owners have more kind of a relative ease to influence. And then I think thinking towards the future, I think delivery models that are different, or thinking about how equipment is purchased or provided. Owner champions are, I think, essential to helping make these initiatives happen, and to help to work with procurement or work with funding incentives with facilities folks, looking to other institutions for what they're doing with some of these smaller pieces of equipment, or how research happens and how users are actually finding ideas to save energy. I think some of that can happen with some of these industry groups and conferences that are out there. I think there's a lot of good resources and a lot of really well-intentioned people that work throughout kind of a spectrum of roles within a research facility and research facility design and operation, that they're sharing stories. They are just wanting to find ways to help reduce energy, make labs greener. So, in summary, I think, there's a big opportunity to be on a trajectory towards significant savings. I think as an industry, we've really come a long way in terms of what we've accepted or are willing to consider for, say design solutions. And we've gotten to the point now where I really do think as design professionals, we've been able to find a lot of the savings and provide that to the owner. And now we get to a point where I think we even need more owner engagement to understand how do we push further? How do we really push into this lab equipment or office equipment element of projects to further find savings? As I mentioned at sort of the outset, I think there's a real challenge though, as we have provided a lot of these systems, right? We know buildings inherently get out of tune. In a simple VAV, let's say simple VAV building, right, will get out of tune. And there are many owners who are, sort of staff constrained, maybe capability constrained, and just even operating those is too much. In many cases, they're saddled with a lot of buildings. When we introduce these new systems, we're still at a point where a lot of ideas have been sold and implemented in projects. And as a whole industry, we're really trying to figure out how to operate these buildings better. And so I think there are tools out there that can be used. But, I think it's important that organizations realize if we're going to sort of stay on target as anticipated, there are elements that probably need to be put in place as part of that. I think as part of measuring performance, right, more interaction between the design team and the energy modeler and the owner, more openness to share the utility data and to really ask for some level of review to say, like, how are we really doing? Like, what things aren't we catching? The building is operating. I don't have anything that's setting off flags or alarms, but are we really running optimally, right? So how do we get after that and begin to assess that? And I think as part of that, we're seeing more and more, opportunity to use data, to use larger integrated platforms to not only do the BAS piece, but tie into maybe other business enterprise elements of an organization so that maybe it's easier to sell the investment because all of that data can feed up and help to inform decision making in a bigger way. It's not all about energy. In many cases, it's also about reducing staff time spent addressing alarms or, addressing complaints of hot cold calls. And so I think really looking in a holistic way about how data and some of these new analytical platforms and display platforms could help staff embrace and adopt these new facilities and the changes that come with them and really help to make them successful. So back to the objectives, hopefully for each of you sort of struck a chord with areas that you see, or maybe ideas you've been thinking about, and how some of those fit into, at least the experience I've had over the last 15 years in higher ed and I guess the private sector in doing S&T or science and technology research buildings. I think there's a huge opportunity, for us to continue to push. I would say, I don't see a lot of new technologies coming to the marketplace in terms of new design strategies. For the most part, it's all of us kind of working together to help owners understand how to deal with change. If you haven't built a building in 10 or 15 years, it's like drinking from a fire hose, thinking about everything that's new in the market. If you've been building every 2 or 3 years, and you've been adding one of these in at a time, you kind of, those folks are kind of more in line with where we are. So, again, thinking about some of those tools that will help staff, both operate and really optimize the performance is, I think that when we think of new technology, to me, that is one of the big pieces so that we really do realize these energy and water savings that we are projecting and designing for, but we need to make sure they materialize and that it's sustainable to maintain those savings. So with that, we'll go to questions.
Thanks very much, Paul. That was very interesting. I can't believe the amount of water that goes through some of these things. I'd never really thought of it. And wow, it was an eye-opener for me. We do have a question. I guess the question is, what are the barriers to uptake on an institutional basis? And have you got any insight on how we can break through those?
What are the barriers to institutional uptake? I think you probably say there's a lot of them. I think in many cases, I would say the majority of institutions at least are at a point where leadership has asked for something different, right? And it comes then to, I think there's sometimes there are challenges within sort of the project management, capital projects group. Sometimes it's been facilities. Sometimes it's been EH&S. I think what has been, most successful is just a lot of earlier engagement. And so, I have a colleague and, kind of my mentor for, in my career here who we've spent a lot of time with this. And, 10 years ago, it was a lot of energy models and results and data and results and data. And it felt like we were always trying to make that case. Now, I think as design professionals, we and others out there kind of know the solutions. It becomes more of a change management. And so if particularly, a lot of these are engineering driven. And if we as engineers don't come into the process until SDs or later, it's hard to influence the delivery methods, the timelines on projects, the budgets. Everything's just made it all the more critical for us to engage in that programming or concept phase and begin to explore these ideas. And oftentimes we have more meetings just talking about those strategies and working with EH&S and facilities and talking through systems, maybe connecting them with vendors and or other peers so they can understand them, so that process can happen at a point in the project where you really have some time to course correct if need be, or if all those strategies aren't adopted or deemed eventually deemed not acceptable, right? You still aren't so far that you simply just have to swing back to traditional cut and paste design, right? From a cost perspective, if you can evaluate things earlier, maybe ahead of some of the estimates, you can get better cost trade-offs and try to avoid, fear pricing you might get to a contractor or, from a contractor. I think it's just education and dialogue much earlier, I think has been the biggest, probably the biggest thing that has made projects successful.
Education.
Yeah.
Yeah, it's pretty well that. Well, Paul, that's all the questions we have. So
okay.
I guess on behalf of SLCan, I'd like to say thank you very much for your presentation today, and it was most enjoyable, and we'll talk soon.
All right. Thank you very much to you and others.
Okay. Bye now.